Okay, so I think we can go ahead and make a start now. So thanks everyone for coming along to this Data Science Under the Hood seminar. So for the very first time, actually, we're going to run the seminar in hybrid mode. And thanks very much, Rob. You couldn't have chosen a worse day to make us all come onto campus than today.
My pleasure.
No, but it's really exciting to actually have a hybrid one, which is nice. So let me just introduce Rob. So Rob, many of you probably already know Rob, but he's a postdoctoral fellow in the Models and Algorithms program in the centre. And before coming to QUT, he was a postdoc at University of New South Wales and also the University of Queensland, where he did his PhD. And Rob's research interests are essentially at the intersection of computational statistics and machine learning. So he's interested in many different topics. So let me just read a few out to you here. So we have Monte Carlo integration for challenging problems. We have Bayesian inference for big data sets, particularly for time series. Kernel methods, Markov chain Monte Carlo, variational inference, and also rare event simulation. So without further ado, I think I'll now pass it over to Rob. And Rob's going to talk to us today about normalizing flows.
Thank you, Chris.
Thanks, Rob.
So Chris read the long list of my interests, and now I'm going to talk about something that isn't on that list. So we can add one more. But no, it's great to be here in person. Finally, seminars and normalcy are beginning as they should be again, so it feels good. So more than ever, I think it's important to acknowledge the traditional owners of the land, given that we're here. And that's the Turrbal and Yagara people here at QUT. So I'm going to share my screen now. I'm presenting from an iPad because it allows me to walk around because it's more fun that way. So what am I talking about today? I'm talking about normalizing flows, transport maps, and invertible neural networks. So plausibly, any one of these three terms is really an example of the other to a certain case. So what's this talk about? So in general, in life, as in maths, we deal with the variability of data that we observe via constructing models that involve some sort of randomness. I think philosophically, one could argue back and forth forever about whether randomness actually exists in our universe. But as far as statisticians and machine learners are concerned, the way we deal with the variability and what we see is via randomness. So our talk today is kind of about that. So the way we deal with this randomness is we assume that the data we have comes from some probability distribution, P of X here. And it arises in a manner that our data, individual observations X are random and come from that distribution. So a canonical task in statistics and machine learning is essentially to fit a model of this hypothetical probability distribution to our observed data. And then with that model, allow us to say something about this thing that's generated our data. It's our way of probing it and understanding it. So machine learners call this process unsupervised learning, and that term doesn't exactly mean only what I've mentioned above. It also means learning something about the distribution. But today we're going to be talking specifically about learning that distribution itself, or fitting a model to it rather. And so today's talk is more akin to density estimation, as it is called amongst statisticians. So when you think density estimation, you probably think something along the lines of this photo. So this data here that I've plotted, the little purple dots, what that is this is the famous iris data set. It's about things to do with flowers. So you've got petal width and sepal length up there. Statisticians love this data set. This is probably the most analyzed data set in the history of statistics because every paper with every example does this. But here's an example of what it means to fit a density to it. So behind the data points here, you see this colored heat map. And what that represents is essentially a model that I've fit where the hotter the color, so blue going all the way up to red, represents the model, how much it thinks the probability of getting a point varies. Okay, so even though we've only observed some data in those dots there, we can fit this model, which tells us how we think the random data generating process behaves. So it thinks, there's still, even though we didn't get data here, it thinks there's a possibility of getting data there. Well, it thinks of getting a possibility of getting data there. Okay, so in a sense, it allows us to generalize beyond what we've seen using what we've seen or attempt to do so. So that's kind of what density estimation means in a classical sense. But to a machine learning person, density estimation might mean learning the probability distribution of pictures of people's faces or learning the probability distribution of pictures of cats. Yep. This is still some very complicated object, and you would agree it varies. You take a different picture, you get a different picture of the last one. Okay, so it's not actually random, but the way we deal with variability in mathematics is by modeling it as randomness. So plausibly, density estimation, one could argue, appeals to being used just as much in modeling pictures of people's faces as it is in modeling where the points of my iris flowers characteristics lie. So this kind of brings me on to a kind of related topic, and that's, so why would we do it? What is the interest in kind of modeling pictures of people's faces? Well, this is just an example of a really hard density estimation problem, but the machine learning community is kind of obsessed with generating new pictures of people's faces, but having the models dream up new people. So this person and this cat actually don't exist. They're dreamt up by a machine learning model for the probability distribution on those things. Okay, so the sort of techniques we're looking at today will be able to cover equally as well cases like this and cases like this. Okay, so this talk is primarily about a class of techniques that allows for the construction of very flexible families of probability distribution. Okay, so this is something maybe statisticians and machine learners have been doing for a long time. What makes the techniques we're talking about today special is a few things. The first is we can actually compute its likelihood function when we fit the model. So the classic way of fitting a model is maximizing likelihood. As statisticians, this is something that's often taken for granted. It's like, don't all models have likelihoods? No. In machine learning, a lot of the fancy models for pictures they've had for many years have not had likelihoods that you can evaluate. You have to use all sorts of interesting techniques to fit the models. Another thing that we're going to have is generation from the fit model is computationally tractable and direct. This is nice because it means we can simulate from the fit model and create new plausible scenarios. If you are looking at images, you can dream up new people. If you're looking at the iris flower set, maybe what you want to do is generate a new data set that looks like it, so you can understand the randomness. You can do that with these two. We want our models to scale to very high dimension and capture all sorts of complicated dependencies. This is sort of really like the holy grail of distributional modeling. You want to be able to model anything, no matter how complicated the elements of it are related. And another benefit is it involves deep learning, which is all the craze right now. And I'll talk more about that shortly. Okay, but what is further really special about the techniques we're going to be talking about is it allows us to fit our model, but our model itself, when we fit this model, it's equivalent to learning a way to transform our data. So when we transform it, it has some prescribed simple distribution. For example, a multivariate normal independent distribution. So not only are we learning a model, we are learning a transformation that turns something very simple into the very thing that's generating our data. Okay. So my goal today, with a very interesting photo there, is I want to provide an introduction to this topic. Okay, so I'm going to start with some simple cases and gradually build up to some more sophisticated approaches. We'll start off really simple, but by the end there'll be functional analysis on my slides. It'll be fun. But still, what we've talked about today are only a glimpse of some of the work that's being done both in the stats and machine learning communities. So I put this picture of the bear here sitting on the iceberg in kind of, alluding to this is really the tip of the iceberg. In fact, I would even say there are multiple kind of streams that this iceberg takes underneath here. So after today, whether you're the bear, so whether you choose to dive into that water and explore that iceberg is up to you, but you're kind of getting the bit that's sticking out and everyone can see. Okay. So shall we begin? So flow-based models, normalizing flows, transport maps, they all have similar things, are models that arrive from transformations of some simple base distribution. Okay, so usually in practice, that base distribution is a multivariate standard normal. Okay, now you can all agree that's an easy one to simulate. If you use MATLAB, you type rand_n in and you're done. You put a number inside that rand_n, you get a high dimensional one. Nice and easy. And now we're going to consider some function t. Okay, so for a general function t from p-dimensional space, so if z's p-dimensional, mapping to q-dimensional space, we're going to have this thing x, which is what happens when we feed z into our function t and see what it spits out. That's going to implicitly give us some other random object. Okay, a transformation of something that's random is itself random, unless it's a trivial transformation, like the one that always maps to 0 isn't really random, right? But for most cases of interest, this is going to be a random object here. So in principle, and this is the underlying idea of what I'm talking about today, is if we had a very flexible class of functions t that had some parameter theta. So basically for a different theta, you would get a different function. And we could compute its likelihood for all theta. And what we could do is we could fit our samples using that likelihood via maximum likelihood. So this is kind of a common approach in statistics. All I've said now is we want to formulate our model this way. And in order to have our model take this form, it's not enough to just say, here's a T or here's a family of T's. We need to be able to work out what the probability distribution of that X is, that T of Z. Okay. So for the right choice of T, which has some theta involved with it, we can accomplish the above even in very high dimensions. Okay. So generally speaking, if the random vector Z has some probability distribution, let's call it mu, then X, which is the transformed version of Z, has some other probability distribution mu. Okay. This actually always exists, but it can get very complicated kind of talking about what this probability distribution is. Okay. So to actually talk properly about everything, you need measure theory, you need to talk about change of variables, theorem, image measures, and all sorts of fun stuff. But that's not as fun as I want to keep it today. I want to make it more fun. So we're going to sidestep all of that. And I'm just going to make the assumption today that bold X is a continuous random vector that can take values on all of RD. So we want to model something that just takes values in high dimensional real space. Okay. This saves us having to worry about complicated things involving mixtures of continuous and discrete, or what happens when you only have a discrete random variable. You can handle all these things, but they complicate things. So we're sticking to the continuous case today. Okay. So it turns out this problem here, in special cases of what the distribution of X is when we live in RD, is that we can use a special theorem if we have a function of a particular form. So this theorem looks kind of scary, but anyone who's done calculus at university will realize this is the change of variables theorem from calculus. It's basically the probability version. It's actually the same thing you do when you learn how to integrate on a sphere, for example, but it's just that idea applied to probability densities. So if you have a function T that maps from RD to RD and it's invertible, so for any Z you put in, you can get back. There's some function that takes you back. So you go T of Z, and then there's some function T-1 that will take you back to Z after you go T of Z. If it's surjective, so if it hits all of RD, if it's differentiable, you take the derivative, and it has a differentiable inverse, then we have this theorem, which is a very special case of the theorem for measure theory I was talking about before, where the random vector X, which is equal to T of Z, has the PDF here. Okay. Now, this PDF has this form where this P here is the probability density function of the original random variable Z. Okay, so you just need to kind of invert the function and put it in the original probability density function and whack on this weird thing here. Okay, so this weird thing here is called the Jacobian determinant. So this J is this matrix here, and it's a matrix of all partial derivatives. And essentially, we're going to have a visual look at what that does. Okay, so what that actually does is it looks at the transformation that you've done and investigates sort of at every point how much you've messed with the volume, essentially, because what you're doing is you're stretching space when you do a transformation. So basically, if T takes us here, if I have a square here, you would note that this transformation has turned it into a different object with a different area. Okay, what that J does is if you imagine this square getting smaller and smaller and smaller, what it does is it works out how much the volume's been distorted. Yep, so that's actually what determinants are. It's not always taught that way in linear algebra, but it's the true meaning of a determinant. So as a simple example, if Z has a uniform distribution on 0, 1, I know that violates the assumption that it goes to all of RD, but just humor me. If Z has a distribution that's uniform on 0, 1, then its probability density function is just equal to 1, as long as you're on 0, 1. Yeah, it's the same everywhere, and 0 otherwise, okay? Now, if I take the transformation of 2 of that Z, this is uniform on 0, 2, okay? And it's uniform, so P of X needs to be the same number everywhere, but it can't be equal to 1 because when you integrate 1 from 0 to 2, you get 2, right? So basically, this is a simple example that shows you why you need this term here, because it corrects for the fact that you're messing with the volume. Okay. Okay, so enough of the abstract stuff. Let's do a concrete example. Okay, and the simplest concrete example we can do is probably this one-dimensional one here. So if we take a standard normal random variable Z, and we do this transformation here. So this is a transformation parameterized by two parameters. One of those parameters is epsilon, one of those parameters is delta. And the transformation is the shine, this is called shine, which is the hyperbolic sine function, times 1 over delta, times the inverse of that shine function, plus epsilon. That's a little typo there. Epsilon, delta needs to be positive, sorry. Then by the change of variables theorem, we get something that has this PDF here. So this term there is actually the determinant. So it's complicated, and how it warps the space depends on what x you're at, but that's there. So we have the density. And this is the original distribution evaluated, original density evaluated at the inverse map there. Okay, so this is actually a famous distribution. It's been around since the late 2000s, and it's called the shine arc shine distribution. And this is actually how you construct it. So if you read the original paper, unfortunately, you don't get papers in journals like Biometrica, which is a really, really good journal, just by dreaming up new transforms. This one had some very special properties, which is why it's of interest. But it is an example of one such distribution that you can get via transformations. So what I'm going to do now is I'm just going to stop the share here, and I'm going to change the screen that I've shared. I'm just going to do my journal screen there. And I've prepared a little treat, which is this web app here, which of course has crashed. This web app here, which kind of shows you how this transformation sculpts you a distribution. So you remember, so what we're doing here is this is a slight extension of it. This is the location scale version of the shine arc shine distribution. So we're adding some constant mu, which is going to be its mean. Or not actually its mean, but it's a location parameter, and sigma, which is a scale parameter. So we have these four parameters here, and we can see what the distribution looks like for this transform for different values, right? So if we move mu and sigma, this is just like moving a normal distribution. It's making it thinner or fatter when changing where it's centered. But the magic of this, the way we've used epsilon and delta here is epsilon allows us to skew this distribution very nicely to either side, and delta allows us to make the tails heavier or fatter. So this is an example of a one-dimensional distribution that you can get out of doing a invertible transformation in one dimension, just from something simple. Okay, so this is the best one-dimensional distribution if you want a unimodal thing. You can, it's quite flexible for only 4 parameters, which is really good. Okay, are there any questions at this point? Okay, so David asks, is there something similar you can do to define the number of modes? Not for the sine arc sine transform, because that's just one transform. So one of its nice properties is you can prove that it's always unimodal. Sometimes, because they derived hypothesis tests and stuff for the skewness in the paper. So that's an important property to have for your theory. In generality, there are bimodal versions. I'm not sure if I can think of any that arise from transformation though, but you'll see some later that from more machine learning approaches. Cool. Okay, so that's my beautiful app. So let's do another example, okay? This is in D dimensions, okay? I want you to start with the standard normal Z, high dimensional standard normal Z, zero identity. And now the transform we're going to apply is parameterized by the vector mu and a lower triangular with positive diagonal matrix L. And this is the transformation there. Okay, so you can actually show, and I hope this is something everyone did in second year statistics. I think this is what I did in second year statistics. You actually use the change of variables theorem, and you show that if you have this, then the X is actually a normal distribution with mean vector mu and covariance matrix sigma, which is L times the transpose of L. Okay, actually, the way you define the multivariate normal distribution more generally actually involves a transform like this. From memory, it's defined as like the normal multivariate normal is anything that arises as a transformation of a certain form, and it can actually be singular here if L isn't obeying certain properties. But I'm giving you the nice version there. Okay, so that's nice, but I've only told you how to get a normal and some boring univariate thing, right? I mean, I think the sine arc sine is quite exciting, but for some reason, no one else ever does. So let's have a look at what we can do now. We've learned 2 transformations, okay? So what we can do to make our distributions more flexible is we can compose these transformations, right? If you can do it for if you can do it for one transform and get its density, you now have the density. So now you can do another transform and use change of variables theorem to get its density again, right? Life is good. So if we take this example, if we have a standard normal, we're now going to have some intermediate value of Z1, which is going to be some matrix times Z. Yep, so this is transforming a standard normal into a multivariate normal with a certain covariance matrix. And now what we're going to do is to each individual element-wise, we're going to apply a sine arc shine transformation. Okay. So what does this look like? I'll show you. It looks like this. So here's what we start with. Here's the first transformation we do. And here's what happens when we mess with its marginals with the sine arc shine transformation. Okay. Interestingly, what I've done here, it's actually an example of something called an implicit copula formation with the Gaussian copula. So it's kind of, people in stats have been, like this idea has been floating around. It's not something that's necessarily new, but this is kind of the simpler examples of it. Okay, so this distribution here actually has Gaussian dependency, but weird marginals. It's not exactly sine arc sine marginals for a reason I won't go into. Okay, so that's so we call this a flow. Yeah, so you're flowing through a collection of transformations. You go from here with the first element of the flow, and then the second element of the flow takes us there. Okay. So basically, the nice thing about flows is they go in two directions, right? So if you want to simulate the flow, it's easy. You draw your initial distribution, and then you just iterate over all the transformations you have in your flow, and you return the last thing you get as a sample from that distribution. Now, if you want to work out the log likelihood of your flow model for some given sample, you want to score it, you want to say what's the likelihood for this sample with these parameters, you can kind of go backwards. So you start with X, and you take the inverse transformations, and then you iterate backwards, and as you go, you collect the log determinant term. Okay, now to convince yourself that this is true, you kind of need to look at the two transformation case and see that it generalizes to the algorithm I put there. But I'm not going to bore you with that derivation. I just want you to know that there is a nice iterative procedure backwards that you can do. Okay, now this seems a bit tedious, but in practice, we let a computer do it. And in the modern era now, we have something magical called automatic differentiation. So what a computer can do is it can compute the derivative of anything that it does. Yeah. So you can do this algorithm, go down there and then say to it, hey, now what's the derivative with respect to this input I gave you? And so this lets us do gradient descent on the parameters of our flow. So each one of these T's, and obviously has a corresponding inverse, has parameters, and we can fit a model that way. Okay. So the main thing so far is we can get models that are flexible by composing things, and we can fit them and simulate from them easily with this. Okay. So in order to make these models really flexible, we want those transformations to be really flexible, right? They also need to be invertible, but we can cross that bridge when we get to it, right? So what we're going to do is we're going to learn about deep learning first. Now, you probably need to be living under a rock to not have heard about deep learning now, but I'm going to go under the assumption that you've never seen this before and explain all of it in one slide. Yeah? There's only one prerequisite, and that's you know what linear regression is. Do we all know what linear regression is? All righty. The computer scientists are going to kill me, but that's okay. Okay, deep learning. So you're all familiar with multi-linear regression. So this is just linear regression where you have multiple outputs, yeah? Okay, so basically for an individual prediction you want to do there, you can write the vector y is equal to some matrix w times your input x plus some vector b, okay? This is a linear regression model that has multiple outputs. Agreed? Agreed. Okay, now if we want to make this more flexible, first thing you might want to try, you might say, okay, linear regression is pretty good, but we want something more flexible. What you might try doing is go, well, let's compose that with itself. We're not doing normalizing flows here, but maybe just do a linear regression function inside a linear regression function, in which case you get something that looks like this, right? This doesn't help you at all, right? Because when you do a little bit of algebra, you get essentially something here, which is just equivalent to some other linear regression and some other term here, which is equivalent to some other B term. Yeah. So really, if you do this, you're back here and it's game over. Okay. So basically, what you do is very simple. In between composing these two linear regressions, you take some nonlinear function, for example, hyperbolic tan or sigmoid, and you apply that element-wise. So now, this here is called a neural network. That's literally it. It's called a neural network for reasons. I mean, I could draw you a picture, but think of it as just linear regression with some extras thrown in. Yeah, you reiterate that procedure many times. Yeah, so you keep doing W of H of something, W of H of something, W of H of something, W, and put it all inside each other, and you get what's called a deep neural network. Yep. Okay. Even things that people use for images like convolutional neural networks can technically be written in this form here. They're just special sort of matrices. Okay, so that's deep learning. Yep. So why is the hype if it's just linear regression with some extras thrown in? Okay. So the great thing about deep learning is, firstly, it's tractable. So you can train things with gradient descent via backpropagation, automatic differentiation. Okay. It's powerful because the models are highly expressive. They have this mysterious powers where basically, even though you have way more parameters than data points, they really work. They still work well and don't overfit. Okay, so this is a phenomenon that's only become somewhat understood recently why that is, and it's quite actually very interesting stuff. But I don't have time to go into that today, but it's called the double descent phenomenon. But for us today, it serves as a flexible way to parameterize an arbitrary function whenever you need one, okay? We just want a very flexible function that we say, we need a function here in an algorithm, put a neural net in, and we'll learn what that function should be. Okay, so this is a quote that I heard someone say once, but I've co-opted it. And a neural network is the second best solution to every single problem that requires learning a complicated function, right? The first best solution is one that really suits the problem at hand. Yeah, if you know that a function you want to learn is linear, you're probably not going to do better by doing a neural network. Although one could argue with double descent, maybe you could, but let's not get into that argument. Okay, but it's the second best solution to every problem because it doesn't require you to think so much. So the question is now, so okay, Rob, well, that's simple. All we need to do is we just need to get that T we were talking about and make that T a neural net. And if that T can be a very flexible function, we're good. But we've got a few issues. Okay, that T needs to be invertible, amongst other things. Surjective, continuous inverse. The fancy name for that is it needs to be a diffeomorphism. And in general, and this is the killer, determinant computation, you say, oh, it's easy, we just need to add that determinant term. But if you're in a million dimensions, computing a determinant is highly non-trivial. In general, computing the determinant of a matrix, because that's what that term is, it's a Jacobian matrix, requires a cubic computational effort. So a million cubed is a very big number. I think past, I don't know, maybe 1,000, 10,000, you don't want to be computing determinants of general matrices. Yep. So for me, here comes up to me and says, Rob, I got a matrix sitting in my pocket. How much effort do you need to do the determinant? I got to say d cubed because that's going to cover all cases. Yep. If for me, it says to me, well, what if I told you the matrix in my pocket is lower triangular? Well, maybe I can say something different then. Yep. Okay. So we need to be smarter and think a bit. So before we launch into using neural networks, I want to show you a very particular structure of transformations. And this is autoregressive transformations. So basically what an autoregressive transformation means is the first x is only a function of the first z. The second x is a function conditional on the second z whose parameters depend on the first z. Yeah, so we transform Z2 depending on what Z1 was. Yeah, we transform Z3 depending on what Z1 and Z2 are. Okay, so the transforms depend on only things that came before it. Okay, it's autoregressive. So it turns out though, this sounds really restrictive, this class of transformations, but it turns out though that if you think of it, you realize that actually no, you can get a hole in one here and transform anything into anything, subject to mild regularity conditions. You can always dream up funky distributions that break rules, but you can basically, subject to very mild conditions, transform a standard normal into any continuous variable on all of RD by basically choosing these transforms as follows. The first transform, only on Z1, just needs to transform Z1 to be the marginal of the first variable you're interested in. It needs to transform the second one to be the conditional of the second given the first. Yeah, so this is kind of a very particular structure and so on and so forth that basically shows that with one transformation, you can actually get any distribution you want. Yep, and the magic of this is this Jacobian is actually lower triangular. Yep. Because when you go to compute all the derivatives, this only has terms with Z1. This only has terms with Z2 and Z1. This only has the first three and so on and so forth. Okay. So this hypothetical magical map that would translate your standard normal into anything you want is actually called the Canoe Rosenblatt rearrangement. So they were talking about this since the 50s, I think, in the mathematical statistics literature. But it kind of, we're not kind of using the theoretical concept of it. We're just saying, well, it would be nice because it looks like a lower triangular Jacobian map like this, in principle, could be as flexible as we need. So we could almost get a hole in one if we do these T's properly. Okay, so the real kicker here is the determinant's lower triangular. Okay, now we need to impose some regularity to make sure that things are invertible, but let's assume that we have a lower triangular Jacobian whose diagonal elements are all positive for now. We'll enforce this in practice in a second. Okay, if you have this, okay, then you've got an invertible map. There's actually a theorem that shows this. But the main kicker is the determinant computation now becomes linear. There's a big difference between 1,000,000 and 1,000,000 cubed. Right? Okay. So to compute the Jacobian of a lower triangular or upper triangular matrix, sorry, the Jacobian, to compute the determinant of a lower triangular or upper triangular matrix, is just the product of the diagonal entries. Yep, nice. Okay. So we now know some sort of structure that makes the determinant easy, but we still got this invertibility problem. It's like, yeah, Rob, you'd be lower triangular if you did this, but how do you make sure this is invertible? Yeah. Well, I'm going to show you. Well, I'm not going to show you. This has been developed in the last 6 years, ways to do this in practice. Okay. So there's many ways you could do this. I'm not going to go into the variations and why they're important. I picked the one that's kind of the most intuitive and nice. And this is something called an inverse autoregressive flow. Let's not talk about why it's called the inverse, but if you ever look this stuff up, go under that iceberg. This is the inverse one. So this is all you do. You say X is equal to mu1 plus sigma1 z1 for the first element. So that's just a linear transformation of the first element. And then what you do is you do a linear transformation again, but now the mu depends on the z. So it's some function of the z. The sigma is some function of the z1 before it. Yeah. So we're doing linear transformations for each one of these variables, but the parameters of that linear transformation, the mean and the standard deviation we're scaling it by, depend on variables that came before it in the order. Okay. Now, this is neat because it's trivially invertible. Look, you go like, it's almost like back substitution. You just go in the opposite direction. Z1, you do a little algebra here and you get it. Yeah. Z2, here it is. So once you have Z1, you just go all the way down. So you can invert it. It's a sequential operation to invert it, but assuming you have these functions, it's actually a parallel operation to generate from it, right? Because you just hand me all the z's and I plug the z's in all these functions that need them, and it spits out what I need, okay? So all of these functions here, it would help if they're very flexible functions, right? Does anyone have any idea how we could pick very flexible functions? So it doesn't matter what those functions are, right? It's invertible no matter what those functions are. That's the trick. If you look on the right-hand side here, it doesn't matter what those functions are. It's still invertible, okay? Any ideas how we should make mu k and sigma k to be very general, flexible functions? Did my one slide on deep learning teach you nothing? No? Okay. So yeah, so on practice.
Hey, Rob, you also have the answer on the slide.
Well, I know, that's what makes it extra easy, Chris. Yeah, okay. So mu k and sigma k are all a neural net. Yep. I haven't given the full answer, actually. Yeah. That's a lot of neural nets, right? If we're in a billion dimensions, that's the pixels on a photo. That's a lot of neural nets, a lot of headaches, right? It still scales kind of linearly, but it's a lot of neural nets, which is a bit of a headache, right? The neat thing about this is it's not actually a lot of neural nets. These functions are all a neural net. I've been purposely vague with that because it's a special type of neural net that respects the autoregressive structure of the variables. Yeah. So basically in practice, I mean, it's in this paper here. In fact, in practice, you don't need to worry about any of this. You can just load up PyTorch and say, give me an autoregressive neural net. But in practice, it's a neural net that's made in a special way so that essentially you plug all these things into one neural net and it outputs all your outputs here, all these terms in such a way that it respects the autoregressive structure, which I think is really neat. You don't need to go through a million neural nets, right? So it's all done with. Okay, so let's do an example of an affine inverse autoregressive flow. So here's this familiar friend from earlier. Oh, except instead of mu, I now call the mean mu just to keep things fresh. Okay. So this, what we've got here, the construction of a standard, of a multivariate normal using, this is called the Cholesky factor of its covariance matrix, is actually an example of an inverse autoregressive flow. Yeah. The mu function, the mean for the jth element, is just mu j plus this. This is just the row of this matrix, right? And the sigma j, the scale factor, well, it doesn't care about the things that came before it in the ordering. It just takes LJJ. Yeah. So this is kind of interesting because just like neural nets that we learned before were a generalization of linear regression, inverse autoregressive flows in the distributional sense can be thought of as a generalization of multivariate normals because it's just a more general class of map. This is a very specific and linear one, right? So I always find that kind of fancy, that the multivariate normal is linear. But I mean, that's kind of what makes it special. Okay. So we have one problem though, almost done. We solved the determinant problem, we solved the invertibility problem, but we haven't completely solved the flexibility problem. Okay. The problem with the flexibility problem here is that first variable, it doesn't get any love, right? It's always going to be a normal. Even if I keep composing this transformation, all I'm ever going to do is shift my Z1 and scale my Z1. Yeah. Now you can shift and scale a normal as many times as you want, it's still going to be a normal, right? So unless the marginal distribution of your first thing is actually normal, you're in a bad place. Okay. Another thing is that also these earlier ones, maybe you need a lot of transformations to make these something flexible because they don't interact as much as the later ones. Okay, so the simple solution here is basically just reverse the order of the variables in between transforms. So remember, we're doing a flow, we're doing a sequence of transformations. So we're going to use a whole bunch of these inverse autoregressive flows, but in between, we're just going to reverse the order of the variables. So now the one that got no love gets all the love and vice versa. Okay, so basically your flow here, an inverse autoregressive flow, would look something like this. You do the first inverse autoregressive flow, you reverse things, you do a bunch of other ones, then you keep reversing, flow, reverse, flow. So this kind of gives all the variables a chance to interact in a very flexible way. And at every step, you've got a neural network. Yep. What's nice about reversing things is that it's actually a transformation. It's equivalent to multiplying by a special type of matrix that has determinant 1. So there's really no headaches there with the Jacobians either. Okay, so that's nice. That's one way you can do it. But this is a point where people got in the literature and they said, okay, we need to do better than inverse autoregressive flows. How do let's try to do it in, that hole in one. We can do this with one thing, one transformation if we're smart enough. It's a cop-out to have to keep reversing and going. Because the more iterations you do here, kind of the slower, I mean, it's pretty fast, but the slower it's going to be needed to do many of these, right? So there's kind of two directions the literature took at this point. The first is find a more flexible way to do a lower triangular one. And the second was, can we do something else? And I'll talk briefly about both. So more generally, what we've done before is you've noticed that the kth element in the autoregressive flow is just a linear thing. There's some shift that depends on the one before it and some scale that depends on all the variables before it, right? So the natural generalization of that is to say, well, that's just a linear function, y equals mx plus b, right? Why can't that be some other monotonic and hence invertible function? So what you could do, I invented this, but it's not actually used anywhere because what I'm about to talk about is much more impressive. But you could say, well, now I'm going to transform each individual element by a Shine-Arc-Shine transformation. Yeah. So now I can say the mean depends on everything before, so does the scale, but then we're also going to do a skew and a tail weight adjustment that depends on everything before. So now I have a 4-parameter transformation inside my autoregressive flow. Yeah. And because I do this element-wise, it doesn't mess with my Jacobian again. It's still lit. Okay. So that's kind of one natural small extension. How do you actually, would you do that? Would it work? Probably. It's better than linear, right? It's better than y equals mx plus b. The hyperbolic signs probably be a pain numerically, especially through backpropagation. So essentially what the result they decided on in the literature is actually to use monotonic splines. right? So if a spline is just something that connects points together, a monotonic one is one that makes sure it's always going up. Yeah, if it's always going up, it's invertible, right? Proof left as an exercise to the reader. So here's an example of a piecewise linear spline. So now you need to imagine that what it's doing is it's picking the location of the height. These are called knots. It's picking the height of the knots depending on what all the variables before it was, right? So this is a transformation we're applying element-wise, but the transformation of the spline itself, what that spline is, depends on everything beforehand. This is a bit complicated, so I'm not going to dwell on that much longer. But what I am going to say is this is what it looks like. Density of Z goes in. This is just a spline, a 1D transformation. You get that out. Yeah, so even with a linear spline, you can do some funky stuff. I hope that answers your question, David, about multimodality. So now ZK is piecewise, a collection of piecewise splines, conditional with parameters conditional on the things before. It's really flexible. Yeah, in fact, going even further, I think this is like a paper 2 years ago. There's been another one last year. How do you do even more flexible splines? So you can do things like rational quadratic splines that are actually curves here and force them to be increasing. It's quite nice. So there's some really, really flexible one-dimensional transformations that go inside the autoregressive flows. Okay, so I won't have time, but this is all very complicated. If anyone's thinking I want to use this, you're probably thinking, oh my God, the splines, how am I going to code up all that? It is a nightmare. I'm not going to lie. I've seen the code. But in Pyro, which is a Python package, there is a built-in library of normalizing flows. And it's literally this simple. You kind of tell it the distribution. You tell it what your base distribution is. You tell it what your transformation is. Here's a spline with an autoregressive flow. This tells it how big I want the neural network. This tells you how many knots I want in the spline. And then I do this. And then here's a training loop. This looks very similar to what you need to code when you do a neural net normally. So there's nothing really that special there. And then at the end, that's precisely what I fit to get this, which I thought was quite neat. Yeah. And as you see here, this is a two-dimensional problem with 854 parameters. It has no right to perform that well. Yeah, magic of deep learning. Okay, like you would expect a heavily over-parameterized model to not do that, right? You can fit a mixture of two Gaussians with, what is it, 3, 6, 10 parameters, I think. Don't know off the top of my head, but a mixture of Gaussians could probably be done with 10 parameters. And you can tell it wouldn't do as good as that, right? Think of how two Gaussians would fix that. And this is done it with 854 and not overfit. In fact, I think that fits really nice. If you look closely, you see there's even probability massed out on the island here. Yeah. Cool. So I'm going to do a special mention of transport maps. I'm not going to have time to talk about them today in any detail, really. But I just want to say that at the same time these things were being developed in machine learning, people in like stats and people that worked on Bayesian inverse problems were looking at the similar ideas to kind of speed up their computation in a different way. So a key kind of task in Bayesian statistics, Bayesian machine learning, in fact, and inverse problems is essentially sampling from some arbitrary probability distribution called a posterior distribution. And basically what these people did is they used normalizing flows, but they called them transport maps. It's the exact same idea. I don't think anyone in machine learning realized because their papers are all done with measure theoretic notation. So it's an easy one to miss if you don't know that stuff. And essentially they worked out how you could use these transformations to basically speed up your computation in sampling or approximate one distribution with another using these things. So I don't have time to go into it today, but I've linked 2 papers there and it goes quite deep, that sort of stuff. It goes quite deep without using deep learning, actually, because the way they did it, if there's any theoretical statisticians in the audience, I think there's one, this is really interesting because they did it in such a way where they worked out a normalizing flow that didn't use deep learning and actually was a convex optimization problem. So it has one solution. So you can actually get the exact answer, which would be great to do maths on. They deal with orthogonal polynomials and some very nice stuff. So cool. So last few minutes or so, I want to talk about invertible neural networks. So let's forget all about that spline stuff for a while. That was nice. Let's take a different tack. Around about the same time people were doing splines, people were saying, well, can we, I mean, look, deep learning is good, but as you add more and more layers to become more and more flexible, stuff gets harder to train. Like you've got to be, it's more finicky with optimizing the way your machine learning framework is using its optimizer to make sure it performs well. So you want to kind of get it in less effort. So this is what motivates all these fancy transformations. So people had a different way of thinking. They said, well, instead of just doing extra splines, you're using neural networks in a really weird way with like the auto-regressive thing and then the spline thing, and then the neural network decides what the parameters of the spline are, only dependent on the ones before it, et cetera, et cetera. It's like, why don't you just figure out how to do a normal neural network, like what I described before, yeah? Wx plus b, h of that, times w plus b, h of that, times w plus b. Why don't you just work out how to do a normal neural network, but do it in such a way where you can actually invert it? Turns out it's actually not too hard to do that for a basic neural network, but you want to do it, but they don't work so well, I don't think. So you need to do it in a slightly more complicated way. So I'm going to very briefly talk about invertible neural networks, just because they have really cool maths, and I purposely left it to the end, and I promised some of you that I would only say the word Banach once, and that wasn't it. So let's have a look at two examples of invertible neural networks. Before we do, we just need to learn advanced deep learning. So this is the second graduate course you do in deep learning on this one slide here. And this is something called a residual network, okay? So before our individual layers, because remember we composed all these Gs in our regular neural network, just look like this, right? And now we say, well, we took composition like this, and this is equivalent to what I had written before, okay? What a residual layer is, it's also called a skip layer, okay, is you now add in at the beginning a little bit of what you had and then add the other stuff. So this is equivalent, by putting things in this format here, it's equivalent to saying to the neural network when you train it, at each intermediate layer, you need to learn what the perturbation from the identity map is instead of learning any arbitrary transformation, yeah? This makes it kind of more stable in practice. From a normalizing flow perspective, you can see what's happening here is actually quite nice because it's saying get what you've got already and then mess with it a little bit. Okay, rather than just really mangle it up by doing this too. Okay, so it turns out when you have something in a ResNet format, it's actually harder to show that it's invertible, right? Because I mean, try to invert this, you can't, right? It's not easy in any obvious way. So in cases like this, we're going to talk very briefly about how they get around that. But what's interesting with the fact with these ResNets is if you look at this, anyone that knows anything about numerical analysis and can only think about numerical analysis and never see anything else would look at that and go, oh, that looks like an Euler discretization of some ordinary differential equation, right? So when you do Euler's method with an ODE, you're sitting at some point and then you add the derivative at that point, right? So the research split in two directions. Some people said, well, that ResNet stuff, and ResNet got state-of-the-art image classification performance. Like ResNet is the name of a very particular neural network, but it has layers that look like this. So I call these ResNet layers. So they said, well, what if we did this in continuous time? What if we made a neural net that was an ordinary differential equation that evolved through time? And this was a whole field called neural ODEs. There's lots of papers, probably over 100 by now. It's also very complicated, so I'm not going to go into that. Fascinating, but in practice, very expensive. So we're not going to go down that long and winding road. So that's one way of doing the invertible net. You do a ODE, and your ODE is done in such a way that you can show that solutions exist going backwards. Something akin to that. But another way is to make the individual layers themselves here to make these invertible. Okay. Now, these. Now, looking at it just the way there and saying that's invertible, how do you make that invertible? It's not clear, yeah? You can never actually get the tractable inverse, okay? It doesn't have a tractable inverse. You need to use some fancy maths to know when a solution exists and to construct a way to get it if you want to go backwards. So very briefly, two kind of examples of that. So this paper here was really nice, okay? All they said is, suppose you've got a transformation that has this form here, which is a special case of V should not be there. So say you have something of this form here. Z prime is Z plus some function of Z. Yep. They said, well, as long as that function G, if you take the norm, you can think of those double bars if you've never seen that before as just the distance between G of Z1 and G of Z2 in the normal Euclidean distance. If the distance between any of these 2 points, once you put them through the transformation, is always smaller than the original distance between the 2 points, then this here is in an invertible transformation. Okay, so the reason this is true is it's actually because G is something called a contraction mapping. So basically what it means is if you keep iterating G, it always brings points closer together. That's exactly what this is saying. If this is strictly less than 1, by putting the transformation on 2 points, you will always bring those 2 points closer and closer together. And there's a very famous theorem. It's probably not even right to call it functional analysis because it's metric spaces, but there's a very famous theorem. It's called the Banach fixed point theorem. And basically what it says is if you have a contraction map, so it's about something like this is called a contraction map, then there exists a unique fixed point. Unique, so it's invertible. There's 1 point that solves the equation. Okay. And moreover, the theorem, it's really cute because the proof of the theorem tells you how to get it. And it's via something called fixed point iteration. So basically, now we can construct invertible layers as long as this holds. Unfortunately, it's not that easy to make that hold. But if you make it so that the largest singular value of the matrix W at each layer is less than 1, and there's a reparameterization that lets you do this, it involves some tricky stuff, but you can do it, then you always have a contraction map. So it's kind of very interesting that they use kind of the kind of abstract mathematical theory in order to kind of show when you can get an invertible layer. Now, I think this is really nice mathematically. In practice, it's a bit annoying. So the second last slide on my thing is a paper that came afterwards, which talked about a general approach to autoregressive transforms. And this paper is nice. Not many people ever talk about it. I can't remember how I found it. But basically, it said, all right, give up trying to say this is the exact inverse. You won't get that analytically when you go really, really, really flexible, okay? So what they do is they prove that if you have one transformation with the lower triangular Jacobian and another transformation with the lower triangular Jacobian, then any sum multiplied by some scalar, arbitrary scalar of the two, will also have that property. They showed that any composition of two things that have a lower triangular Jacobian will also have a lower triangular Jacobian. And then they showed that as long as the Jacobian does not have determinant 0, that function will always be invertible. So you don't need to know what it is. You just know that you have an inverse. So this is good because now you can construct arbitrarily flexible things by just composing and adding multiples of lower triangular transformations. So basically what they do in the paper is they say, well, as long as t here is element y is greater than 0, this transformation, it's in terms of x, will be invertible. So this looks like the ResNet bit, but you're allowed to scale it at the beginning, which is nice. And then this looks like a neural network. In fact, if k was equal to 1, this would be a 2-layer neural network, but it's not. You're summing up multiple k's, so it's even more flexible. So I was going to draw a picture of what this actually looks like in terms of a neural network. I gave up. It's too complicated. But what you need to know is it's a really flexible transformation, and you can invert it via fixed point iteration. Similar to the Banach stuff I spoke about before. They give an algorithm. So it's actually kind of quite nifty. And they argue it's actually more efficient because with inverse autoregressive flows, you remember that you got to do it sequentially to invert it. Remember how we looked at that? Yeah, it's parallel to generate, but it's sequential to invert. So they argue that if you need to do d iterations to invert of an inverse autoregressive flow, the fixed point takes less than that and typically gets there faster. So even though it's kind of sounds like it's a dirty way around, it's actually kind of more efficient in practice. So I'm going to conclude there, and I'm going to say we're at the tip of the iceberg. If you want to dive in, I have a present for you. So what you've seen today is a shortened and made technically gentler version of only the first part of 4 of my ANSI Winter School course this year on deep probabilistic models. I added some bit on invertible neural nets because I wanted to give people who've seen it something new. But there is 4 8 hours of lecture content, 2 hours of Jupyter notebooks of implementing some of this stuff. We cover all these things here. I'm going to conclude just by showing you the website. So it's all on my website with the link, and it's quite nice because I put all the lectures on one page, and there's the Jupyter notebooks there if you want to have a look where we actually do that example. So you can learn more about how to do this in practice. Today's been mostly conceptual. But there's a lot there, and it's a lot of fun and covers a lot of things, including some things related to the other uses of normalizing flows. So with that, I will wrap up, and thank you very much for your attention.
Well, thank you, Rob. That was really fascinating stuff. So do we have any questions from the audience, so either physical or online? Lawrence.
Okay, yep, we'll do Mingok first. Yep, so Mingok, hi Mingok. Just a question, how is normalizing flow compared to Copula as method for constructing? Can normalizing flow generate interesting interpretable dependent structure that is of interest to statisticians? If you're aware of any work that compares these two methods, it'd be great if you can share it with us. Okay, thanks for the great question, Mingok. So the challenging thing is there is this intricate link between normalizing flows and copulas because of this implicit copula stuff I mentioned. So there is like, one could technically be an example of another. In terms of comparing, I mean, one's not always an example of another, but in terms of comparing, I'm not aware of anything. I know that these can be useful for generating, for modeling, because I'm in a project now where we're doing some synthetic data stuff, and they seem to work well. They're like, compared to copulas, I'm not sure, but compared to things like GANs, they're way more reliable to train, they're way faster to train, they behave nicer. But in terms of copulas, I think Nadia Klein has a paper where she does some spline transforms. It's actually quite related. So she takes essentially what's a linear inverse autoregressive flow and splines it. So it's not right to say a normalizing flow is better than copulas, because technically those sort of things are normalizing flows as well. So I guess the question would be, like, do the neural nets help? And, you know, how much trouble do you need to go through with the neural nets? Is it worth it? But in my experience, normalizing flows, fitting them to data as a density estimation model is actually really easy. Using them from variational inference, let's just say I spent a lot of my career trying to adapt them to that, and the optimization is pretty horrible. It just, even though it's really flexible, it doesn't necessarily always get a good answer. But it blew my mind the first time I did that iris example, and it worked first go. So I hope that puts some insight there for you, Mingok.
Can you hear me?
I can hear you.
Great. Thank you very much for the really inspiring talk, Rob. I have a question related to the ResNet slide that you showed that was really interesting. I don't think I've seen that before, and this is a bit outlandish, but what you mentioned about it fitting the residuals and then sort of iteratively improving upon the residuals, that made me immediately think of and in terms of stability and robustness and of transfer learning. Do you think there would be applications for that particular method in transfer learning?
Okay, so the reason ResNet succeeds is because basically it helps avoid something called the vanishing gradient problem. Like it keeps the gradients behaving nicely because you're whacking it in there. So in a case, it was invented as this ad hoc thing to just stabilize training of neural networks. And like a lot of things in the field, once that happens, mathematicians go, no, why is this really working? So I'm not too familiar with all the theory on ResNet at the moment. However, could you use it in terms of, so it learns a perturbation of the identity. Yes, I mean, but so do normal neural nets, they just don't do it directly. So I guess one could only try, because essentially it's an architectural choice. It would seem better suited there, because if you can say I'm doing transfer learning, or it's more tractable cousin domain adaptation, it's transfer learning almost anything goes, then you have some model you fit to one distribution, or some classifier regressor you fit to one sort of probability distribution or response distribution, and you want to transfer it to something else. It would make sense somehow that, because what you are doing is you're trying to essentially learn the difference of just transferring this over with the identity, right? So yes, but whether or not ResNet would magically make it work better, I don't know. That's one to just attempt. But that is a nice connection that I've not thought of. You magnificent scholar, thank you. Okay.
So there is another question in the chat, but we're already 1 minute past 3 now. So I guess that we should probably stop there.
Sure.
I'm sure that you can answer David's question offline as well. So I've got actually also a bunch of questions that I can ask you offline as well. So let's thank Rob again for a really great talk. And yeah, thanks very much everyone for coming along today. So both the people who braved the rain and managed to come in and also to the people online. So I think that's the last Data Science Understood seminar for the year, but we'll be back again next year, bigger and stronger. So I hope you can join us then, and bye for now.